Welcome back, everyone. This is it, the very last lecture of this course. So let's make it a good one. Okay, so last time, if you remember what we did in terms of formation flying, we had derived exact nonlinear equations of relative motion. And then we said, well, those are very accurate. Yes, it's good, but we're not able to obtain analytical expressions for the x, y, and z components as function of time. In order to achieve this, we needed to linearize the equations of motion. So to do that, the process was to apply primarily assumptions on the motion. The first one of which was to assume that the distance between the chaser spacecraft and the target spacecraft was small compared to the target radius position, so the distance between the target spacecraft and M1. And doing so, we obtained a set of three equations of relative motion, yet that are still nonlinear. Okay? So nonlinear equations of relative motion valid for x, y, z much smaller than the distance between M1 and the target object. So how could we then further simplify these nonlinear equations of motion to obtain what we're looking for, which are linearized equations of motion? Well, the trick would be here to assume that the target spacecraft is on a perfectly circular orbit, regardless of the chaser spacecraft orbit. Okay? Only the target spacecraft has to be on a perfectly circular orbit to keep going with the simplification of those equations of motion, which means that we're going to look at theta dot is going to be equal to a constant, and turns out that that constant is going to be equal to the mean orbital motion n, obviously. And then we're going to get theta double dot, or the angular acceleration of the spacecraft, the target spacecraft along its circular orbit, to be equal to 0. Okay? Furthermore, RT is going to be a constant, because RT again denotes the position or the distance between the target spacecraft and the primary body, M1. So if we are evolving along a circular orbit, well, that distance obviously remains constant, such that the terms mu over RT cubed in those equations of motion will be replaced mu over RT cubed is going to be equivalent to the mean motion n squared, because the mean motion was equal to the square root of mu over r cubed from before. So these are the things we're going to simplify these equations with. Okay? And to do that, let me use the magic of the board. I'm going to use the red marker to highlight the modifications I'm about to do and I'm going to be doing to those equations. Okay? So first up, here, theta dot is going to be replaced with n everywhere. Theta dot, n. Theta dot square, n square. Theta dot square, n square. My mu over RT cubed, I said that that was equivalent to the mean motion n square. So this becomes n square. This becomes n square as well. and I said that my angular acceleration, theta double dot, the target spacecraft along its circular orbit was 0, such that this term altogether becomes 0. This one is 0 as well. Oh, and that one here was my n squared term. And just like that, I've simplified everything I could in those nonlinear equations of relative motion valid only under this assumption to linear equations of relative motion. Okay, so let me just rewrite these equations a little bit neater, and specifically I'm going to further cancel a few things out. So I have here n squared minus n squared, which then drives this term to be equal to 0. I'm just going to report my y double dot here to make it a bit more compact. This term here, 0, I can just erase it. I'm going to compact the equation a bit more, like that. So this is going to be n squared times z. So z double dot plus n squared times z equal to 0. The z component. Now here I have x double dot minus x times n squared plus 2n squared, so that becomes 3n squared. This last term is 0. I can erase it, and that's all I can do with it. So let me just write minus 2n y dot and my 3n squared x minus, and that was x double dot. Minus 3n squared x, yes, minus 2n y dot plus 2n x dot plus n squared z. Yeah, works out. And if you look at what we have here, we have 3 differential equations for which the coefficients of our variables are all constants. All right, because n is a constant number equal to mu over n squared is a constant, and so is n. So is equal to this for n squared. So that's a constant for sure, and that's all we have. Okay, so we have, again, differential equations with constant coefficients multiplying the variables of interest here. That means that these equations are now linear equations of relative motion. Yes, that was the holy grail. This is what we were after from the get-go. Equations describing the relative motion between two spacecraft evolving along their orbit, and furthermore linear equations, because we know that we are able to solve these differential equations and come up with closed form solutions for x, y, z as function of time. These 3 equations are very, very popular whenever you talk about spacecraft proximity operations, where you have 2 spacecraft evolving in close proximity with respect to each other, and where the target spacecraft evolves along a circular orbit. And these have been derived in the 19th century by a gentleman named Hill. So for that, these equations are referred to as the Hill's equations. All right, just always keep in mind that whenever you use Hill's equations to model dynamics of a chaser spacecraft with respect to a target spacecraft, well, it implies that the separation between both spacecraft was much smaller than the distance between the target and the primary body, and that the target is on a circular orbit. Okay, so those two assumptions are underlying to these three differential equations of motion. Good. So that was section 5.3, which was about the linearized relative dynamics. So to solve those equations, you could go back to MATLAB Simulink and use a numerical integrator tool. So you have to solve these equations for the acceleration terms and then integrate those signals twice to get first the relative velocity components in LVLH, and then at the end of the double integration process, obtain the relative position components in LVLH, and then feed those signals back to calculate the terms, get new values for the acceleration, integrate twice, feed the terms back, integrate again, and so on and so on. Similarly to the two-body equations of motion we had talked about extensively in the past, and for which I had drawn kind of a sketch of what a Simulink diagram would look like to simulate the two-body equations of motion. Well, you could take the exact same approach here, where we have a box that calculates those three quantities based on what's coming in. So relative position components and velocity components. We calculate this, and that as the output of the box, integrate twice, and feed back the signals you need to calculate the new relative acceleration components in LVLH, okay? That's one way, but the beauty of obtaining those linear equations of motion is that we could obtain analytical expressions for what x, y, z would be equal to its function of time, okay? So you don't need to numerically integrate those signals, and that is the main advantage of playing with linear equations of motion. And specifically, 5.3.1, we're going to look at what's known as closed form solution to Hill's equations, which again, Hill's equations are your three linear equations of relative motion between two spacecraft on orbit. Okay, I'm not going to do the full derivation for the solutions. I'm just going to give you what they are. So for x as function of time, we're going to get the initial velocity in the Lx direction over n times sine of mean motion times t minus 3. The initial position of your chaser spacecraft with respect to the target spacecraft along the Lx direction plus 2 y naught dot over n. Those two combined together. This multiplies cos nt plus 4 x naught plus 2 y naught dot over n, like this. This is for the solution to see how this relative position component would evolve with time, starting from t equals 0 and plugging in the initial conditions in terms of initial position and velocity components. You could just calculate it from t ranging from 0 seconds to 6,000 seconds and see the time history, or generate the time history for that particular component here. And we have also solutions for y and z. 6 x naught plus 4 y naught dot over n sine nt plus 2 x naught dot over n cos nt minus 6n x naught plus 3 y naught dot multiplies t plus the last term I promise, y naught minus 2 x naught dot over n, like this. And finally for z, thankfully this one is simpler than the other two expressions. It's just going to be z naught cos of mean motion and t, mean motion of the target object, target spacecraft obviously, plus z naught dot over n times sine of n times time. Okay, so those solutions to Hill's differential equations also have a name, and they're referred to as the CW equations. CW because the explicit closed form solutions to the differential equations that was developed by Hill were obtained by two gentlemen whose last name were Cloesy and Wiltshire in the context of the Mercury and Apollo space programs back in the 50s and 60s era. Okay, so Cloesy-Wiltshire equations, or CW for short. Now, a couple of interesting things about those three equations. Okay, I'll let you think about it for a while, and then I'm going to give you the interesting facts about those three closed form equations that describe again the time evolution of the x, y, z component of the relative position vector rho as seen in the LVLH reference frame. Okay, so first thing to notice is that the motion along LZ unit vector, which is the Z unit vector of LVLH obviously, is completely decoupled from what's happening in the XY plane. Okay? Is decoupled from motion in LX/LY plane. Right? Everything about Z as function of time is only function of the initial conditions on Z variables and function of the mean motion of the target object. So whatever happens along LX and along LY unit directions is not influencing the motion about Z at all. Completely decoupled. And vice versa, if you look at those two equations, you see that X is only function of X initial conditions and Y initial conditions, and Y is only function of X initial conditions and Y initial conditions as well. So those two aren't function of Z initial conditions. So we could say that and the motion in Lx, Ly plane is coupled, right? Because I just said that x is a function of x variables, but also y variables. So x, y are coupled together. That's all I wanted to say here. What else? What else is interesting? By the way, the motion here you see is actually the motion of a harmonic oscillator. Oscillator. So you, as a designer, you pick the initial conditions of the position of the chaser spacecraft with respect to the target spacecraft in LVLH along the LZ direction. This is what this denotes. And same as the initial velocity in that direction. We let the spacecraft go. And if you just look at the motion in this particular axis, which is normal to the orbital plane in which the motion is taking place, you're going to see the relative motion just drawing an oscillator centered or about the origin, which is 0. And in LVLH, the origin is actually at the target object. Okay? So that's what you would see here. Now the motion in the x-y plane is quite a bit more complex, as seen from those two long equations. But there are a couple of things to notice here. First off is that if you look at y, there is something particular in that specific equation that you don't see in x, and that is that you have a term that directly multiplies the variable t. Okay? And you don't see that in any other equations here, because t is always within the trig functions. So it keeps things bounded, okay? But here, because t goes from 0 seconds on orbit to a bazillion seconds, right? Over multiple and multiple orbits, t would keep increasing and increasing, which means that this term will go from 0 at t equals 0 to infinity. And that would drive the relative position along the Ly unit direction to eventually diverge, okay? Or in other words, the two spacecraft, which would start very close to each other in LVLH, they would start to drift along one axis. And specifically about the Ly direction, you would see a linear drift that would keep increasing with time. So the formation would drift apart, essentially. Or in other words, unless you apply corrective maneuvers, passively the spacecraft would just drift apart and you would lose the formation. So that's not a good thing. So what we want to do typically is to figure a way to cancel this bad term here, which is known as a linear drift, okay? With time, linear drift along this particular axis. So this is a bad effect. So we want to cancel this out. Let's just keep that in mind for what's coming up in the next subsection. Okay? Another thing to note, let's do it in blue, just for the fun of it, is that the relative motion x, y, z isn't actually centered at the target object because you have constant offsets. Okay, so those offsets are not growing with time because they aren't being multiplied with t, but they're there and they're just annoying. Because it means that if you were to look at the motion in LVLH, just a quick sketch of it. So if this is Lx radially out, and then so this is obviously the target spacecraft at the origin of LVLH. That will be Ly in the direction of motion of the target spacecraft, and Lz out of the board pointing at you, at this. Well, you would see the motion of the chaser spacecraft with respect to the target spacecraft to be something that isn't centered about the target spacecraft. So for example, we're going to look at different formations in a couple of minutes, one of which is an in-plane elliptical motion, so an ellipse in the Lx, Ly unit vector. So if you don't cancel those two offset terms, we would see the relative ellipse in terms of relative motion in LVLH to not be centered at the target object. And that could be kind of annoying. So in practice, people like to also cancel those two terms, which is just a constant offset of the relative motion seen in LVLH. Okay? So I think that this is what we can conclude for now in terms of the closed form solutions to Hill's equations. Okay? And again, everything we just said here is under the assumption that x, y, z are small compared to RT, and that the target spacecraft evolves along a circular orbit. Okay? So now that we know, or we've gained better insight in terms of what would happen if things in terms of initial conditions aren't set properly, so we're going to get a linear drift and we're going to get a relative motion which isn't centered at the target, and again that's kind of annoying. Let's see how can we make things better work to our advantage. So that'll be in 5.3.2, which we're going to look at how to obtain bounded relative orbits. Because again, if you were to look at LVLH as a reference frame, Lx, Ly, Lz pointing at you. Okay, so this assumes that the Earth is somewhere here. RT position vector looks like that. So we have the target spacecraft here, and so riding along its orbit like this, and you have another orbit where the chaser spacecraft exists. Okay, so both spacecraft evolve along their respective orbit, seen from the ECI reference frame centered at the Earth here. But if you were to look at just the relative motion seen from the target's point of view, all right, so we forget about the Earth because that's not what is interesting here, but rather the relative motion, and like this. If you don't cancel the linear drift term that was part of the y equation, remember that is the term that was multiplying time, and again because time goes from 0 to infinity, you would get y to just explode as time goes by. So you would get, you drop your chaser spacecraft here, say behind the target spacecraft, it doesn't matter. But what you would see is that the relative motion would start, and it would look something like that in LVLH. But then as time goes by, you would see the y component, or the separation between both spacecraft in this direction, to increase and increase and increase. So you see how the chaser is kind of now far away from the target spacecraft. That is because there's a mosquito or something here. That is because the linear drift term, which was inherently part of the y solution of the differential equations of motion, didn't get cancelled. So that's not good, because formation flying implies that both spacecraft will continue to operate in close proximity as time goes by. Otherwise, it's no longer a formation, it's just two individual spacecraft orbiting the Earth. So what we want to get is a bounded relative orbit instead, that over multiple orbits of both spacecraft around the Earth, we would see in terms of relative motion in LVLH, with target always at the origin of LVLH. Would like to see something that does this and then repeats itself, okay? Such that both spacecraft always stay in vicinity to one another and that the relative motion is bounded, okay? It doesn't go unstable, or in other words, it doesn't drift indefinitely. This is good design. So how can we do it? Well, all we have to do to obtain this is to go back to what was causing us a problem in the XYZ equations of relative motion in terms of the closed form solution and cancel the linear drift term. So we need to cancel the linear drift, which was the term multiplying time. So we had 6m x naught plus 3 y naught dot. That was multiplying time. So if we want this to be equal to 0, it means that, okay, so this is bad, sad face. But if you were to select the initial components of your velocity vector in LVLH in the y direction, so this is what this denotes, y naught as in initial conditions in terms of velocity, exactly equal to minus 2n of the target spacecraft times the initial position at which you drop this chaser spacecraft with respect to the target spacecraft along Lx unit direction. This is what x naught denotes. And then you substitute this back in here, you clearly see that you get 0 for this term, and that makes you happy because that just created a relative motion, or the motion of the chaser with respect to the target spacecraft in terms of LVLH. That would look something like this, something bounded that doesn't grow with time. And you're able to achieve that solely by selecting the initial conditions properly, okay? At t equals 0, where do you place the chaser spacecraft and what is its relative velocity with respect to the target spacecraft, okay? So the remaining of this chapter is just to look at how can we carefully handcraft the initial conditions such that we're able to obtain exactly what we want in terms of relative motion. But no matter what we do, for sure, we do want to end up with a bounded relative motion. So this will always be the case, otherwise, unless specified otherwise. But, okay, you do not want to have the relative motion that grows with time. Otherwise, again, it's no longer formation flying. It's just two spacecraft orbiting along their respective orbit. So this is used to cancel the drift. And furthermore, I said that it could be, or it is often beneficial to have the relative motion, whatever it ends up to be, a circle, an ellipse, a 3D ellipse, like a football orbit, whatever, centered at the target spacecraft. So centered relative motion, or centered, i.e., about the target spacecraft. To do that, you need to go back to the X, Y, Z Cloash-Wilshire equations, which are the closed form solution to Hill's differential equations, okay? And look at the constant offset terms that I had boxed in blue, I believe, and cancel those terms out. I'm just gonna go back here. So the constant offset terms where y naught equal, or y naught minus 2 x naught dot over n. That was the bad terms in the Cauchy-Wilshire equations. That wasn't too good, made you sad. But then, you know that all you have to do is to carefully select the initial conditions, and in particular, if you were to select the relative position along Ly, unit direction, to be equal to 2 times the initial velocity about Lx over n, and that will cancel the constant offset term. And that is great. Happy face. And that's what you have to do. So as a spacecraft engineer or designer of a formation flying mission, always make sure that if both spacecraft are operating in close proximity and thereby the Hill's equations are a good approximation of the actual motion that's going to happen, you do want to place your chaser spacecraft with respect to the target object such that these initial position and velocity about the Ly unit direction are being satisfied. Otherwise, you're going to get a drift and then lose your job, probably, because then the multi-million-dollar spacecraft formation flying mission is just useless. And also you want to center the motion about the target object, such that, for example, you always have the target object within the field of view of your sensor. It could be a good thing to do, or always maintain good communication between both spacecraft, things like that, for practical reasons. But those two things are kind of the underlying or the inherent thing you do want to go from the get-go in terms of selecting the initial conditions for whatever type of relative motion you are trying to generate, okay? So if you enforce those two constraints into the Cauchy-Wilshire equations, you're going to end up with much cleaner equations that would look something like x equal to x dot naught over n sine nt plus x naught cos of nt, and then y function of time equal to minus 2 x naught sine nt plus 2 x naught dot over n times cos nt. And finally for z, well, z is just the harmonic oscillator again. Z naught dot over n sine of nt. So those equations now describe the relative motion you would see if you were to drop the spacecraft, the chaser spacecraft, with respect to the target spacecraft exactly at this location with respect to the Ly direction, and exactly with this speed along the Ly direction as well, okay? And therefore you would see that kind of motion with time. What does that look like? To get a better understanding of what this kind of motion looks like in 3D, all we have to do is to reparameterize those equations as follows. So those could be written as xt equal to minus a naught cos of nt plus some offset alpha, y of t equal to 2 a naught sine nt plus alpha, and then z is equal to b naught sine of nt plus beta, where the a naught, b naught, alpha, and beta are just some integration constants, okay? So I've just essentially reparameterized these equations using different definitions for my integration constants, and specifically my A naught, B naught, alpha, and beta are all related to the initial conditions we had before. Okay? This, 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 and that. But specifically, I'm going to say where, because you need to know the relationships to go from initial Cartesian position in LVLH and initial velocity in terms of Cartesian coordinates in LVLH to those new integration constants. I'm going to say where your A naught is actually obtained as being the square root of x naught dot over n, this being square, plus x naught square. Similarly, B naught is just obtained as the square root of z naught dot, the initial velocity along LZ, relative velocity, I should have said, square, plus initial relative position along LZ, square. Okay, my alpha is arctan of minus x naught dot over n times x naught. And finally, my beta, my last integration constant for the resulting motion, is going to be tan minus 1 of z naught dot over n z naught. And hopefully that was still within the frame of the camera. Yeah, I think so. Okay, otherwise, do not fear. All of this is part of the lecture notes, but because I know that you're still following along and writing down all the equations I'm writing on the board, obviously, right? Don't cheat on me here. I'm counting on you. All right. So yeah, what does that look like then? Well, it turns out that this is better understandable compared to that in terms of figuring out what the relative motion is in 3D space, okay? So just by looking at these three equations, we should be able to determine that the three-dimensional motion of my chaser spacecraft with respect to my target spacecraft is such that its projection in the LX LY plane corresponds to an ellipse, okay? Because X and Y coupled together would create not a circle but an ellipse, and the reason for that is that the norm of the cos and the sine terms is not the same, right? This is twice as big as A naught, and that's why we have an ellipse. And this projection is coupled, which is then coupled to a simple harmonic oscillator in the LZ direction. Okay? Do I need to draw this in 3D? Uh-oh. hopefully not. Just want to make sure that there's no empty figure for this. No. Well, let me just attempt it nonetheless. Okay, it's going to be probably a catastrophe. I'm going to crash and burn here, but let me do the best I can. Because I know it's not easy the first time you play with three-dimensional motions in Earth orbit and furthermore relative motion. So seen from an observer sitting on the spacecraft orbiting its own orbit around the Earth. And now we're talking about ellipses, oscillators. So, yeah, I know it's not easy. I've been there as a student myself. It just takes time and practice. So the more you're going to play with these equations, the more you're going to do simulations, the more you're going to look at them and try to wrap your mind around it, the better you're going to get at figuring things out in 3D space in terms of relative motion, okay? So, let me draw LVLH. And the reason why I draw this reference frame with this organization is that for myself, I always pictured the Earth being down here with the position vector of the target spacecraft, which is dead center at the origin of LVLH like this, such that LX is radially out. And I picture the spacecraft to be orbiting towards the left. And this is why my LY unit vector is here. And my LZ is normal to the orbital plane of the target spacecraft and is therefore looking right at you. Okay, Z is out of the board like that. So the motion, the relative motion of the chaser spacecraft, which just keeps orbiting its own inertial orbit with respect to the Earth, right? It's not as if the spacecraft is actively doing an ellipse around the target spacecraft, right? So if you have the Earth here, all you have are two orbits, the one of the chaser, and we said that the one of the target was a circular orbit, something like that, okay? So you have two orbits in terms of inertial orbits with respect to the Earth, or the ECI reference frame that has its origin in the Earth, okay? So we said, is it clear? No, let me do two things simultaneously then. This is the relative motion, or seen from the target spacecraft perspective, but seen from an observer on the Earth. So this is the Earth. You would get the target orbit, which we said was assumed to be circular, like this, right? That's the Earth, North America, Quebec, Florida, Central America, South America, hopefully it's clear. Have Europe over here, part of Africa, whatever. Okay, that's the Earth. Not too bad, actually. This is the target orbit around the Earth, which is circular. That was our underlying assumption from this point on. The chaser orbit could be whatever in terms of shape, but let's assume that it is slightly elliptical. I'm going to do something like this, maybe. Oh shoot, I want to do it in another color. Let me do black. Okay, so the chaser orbit in black is an elliptical orbit around the Earth. Target orbit in red is a circular orbit, like that. So both spacecraft just happen to be orbiting around their own orbit, or respective orbit. But if you were to be sitting on a target which does this, and look at the chaser as they come close and further away and closer together and further away and things like that, you would see an elliptical motion that would be drawn from that perspective, okay? From that perspective, or the 3D motion projected in the LX, LY plane would be that of an ellipse, like this. But again, it's not that the chaser is actively orbiting around the target like this, okay? Some people confuse the relative motion with the inertial motion. That's not what's happening. It's just impossible without expending an outrageous amount of fuel. Okay, so both spacecraft are just coasting along their orbit, but if you'd be sitting on a target and looking at the chaser coming above you, coming behind you, in front of you and all that, it would be drawing a relative motion that looks like an ellipse in the LX, LY plane. So that's the three-dimensional motion that would be taking place projected on the LX, LY plane. So that is that of an ellipse. And the relative motion along the normal direction to the orbital plane of the target spacecraft, so along the specific orbital angular momentum vector of the target spacecraft, essentially, right? So that is the motion towards you, away from you, essentially along this direction, LZ, would be just an oscillator that goes back and forth. So back, forth towards you at the origin, past the origin, so back and forth like this, okay? So that would be oscillatory motion along this direction of the motion being projected on this direction. So essentially, it just draws like a three-dimensional ellipse over time. That's what it would look like, okay? And the reason why it's an ellipse here, not a circle, is because if you were to go back and look at the reparameterized closed-form solution x, y, z in terms of A naught, B naught, alpha, and beta, you would realize that the magnitude of the relative ellipse seen in that perspective is your A naught, that this is your 2 A naught, and that the extent to which the relative motion goes back and forth along this direction would be your B naught, like this, okay? And alpha and beta only characterize where along this three-dimensional shape is the chaser spacecraft being initialized. Is it starting from here, from here, from here, or from here, okay? So those, the initial position along the three-dimensional relative orbit is actually just selected in terms of the alpha and beta, which were the two last integration constants of the reparameterized equations of motion. Okay? All right, so another thing to discuss before we jump into the actual engineering work, and that would be to look at 5 different designs that we can use to generate bounded relative motion, because this is the most generic relative motion we can obtain, just by looking at the shear equations of motion, but by selecting the remaining 4 initial conditions, because 2 of them are kind of set in stone to give us a motion centered at the target and bounded over time, so no drifting motion. So we have 4 other free parameters, if you will, to play with, and depending on what we chose, or what we're going to choose for them, that will generate a different relative motion, okay? But one last thing that I want to quickly talk about is the relationship between relative orbital elements and initial conditions, Cartesian initial conditions. And one thing that is super interesting is the fact that the non-drifting condition we had looked at in the past, non-drifting condition, which was our initial speed along LZ, along LY, sorry. Choose it to be minus 2n x naught. to cancel the drift. This, in terms of orbital elements, or relative orbital elements, which is the difference of the orbital elements between the chaser and the target spacecraft. This actually translates into difference in semi-major axis to be exactly equal to 0. Oh my gosh, that makes so much sense, right? Because if you remember our definition, or the second definition we had for the specific orbital energy, which was your v squared over 2 minus u over r, well, no, that was the first one. The second one was the mu over 2a, I believe, for the orbital energy, or something close to that. Anyway, we had a relationship that was giving us orbital energy as a sole function of the semi-major axis. And now we just said that if we want to generate a non-drifting relative motion, we have to ensure that the difference in semi-major axis between the chaser and the target orbit has to be equal to 0, or in other words, that they must have the exact same amount of orbital energy. Because if one spacecraft has a greater amount of orbital energy compared to the other one, well, the formation will drift apart. And that makes a lot of sense, okay? So to make sure that we get this is only a matter of making sure, this is M1, that the radius of the circular target orbit, and try to draw a proper circle for once. Not this time. So pretend that that is the circular orbit of the target, because again, the target is always on a circular orbit for this kind of analytical development. That's kind of the semi-major axis, if you will, of the target object. While the orbit for the chaser, which in its most generic form would be an ellipse, has to have the same semi-major axis, yet could be of a different shape. Okay? So the radius of the circular orbit needs to match the semi-major axis of the chaser spacecraft orbit. Otherwise, the relative motion will completely drift apart along the Ly unit direction. Okay? So just an interesting fact here and something to keep in mind. Another thing to look at was the no offset condition to ensure that the relative motion is actually centered at the target spacecraft or around the target spacecraft. And that was, in terms of Cartesian initial conditions, that was our y not equal to x naught dot over n. Turns out that this, in terms of orbital elements, translates into a difference in argument of latitude equal to minus the difference in right ascension of ascending node times cos of inclination of the target orbit. Okay? Now, this one isn't obvious at all. This is just a fact, okay? But something to keep in mind should you ever try to derive relative orbits in terms of relative orbital elements instead of Cartesian initial conditions. This is what this translates into. But that one is very important to understand. Okay, that one not so much. It's just for you to know. Another thing is that the size of the projected ellipse in the LX-LY plane is related to a difference in eccentricity and difference in inclination. How? Well, it can be shown that the semi-minor axis of the projected ellipse onto the LX-LY plane, and by the way, this is half of the semi-major axis of the same ellipse is actually equal to the semi-major axis of either spacecraft, because they both have the same semi-major axis by virtue of this difference in orbital energy, which is equal to 0, to obtain a bounded orbit, times the difference in eccentricities. So if we assume that the target spacecraft is along a circular orbit, that means that the eccentricity of the target is 0, and therefore this would just be replaced by eccentricity of the chaser orbit. Okay? And then B naught, the out-of-plane oscillatory motion, is related also to the semi-major axis of either spacecraft times the difference in their inclination. Okay? So difference in inclination creates this out-of-track motion, or this cross-track motion, whereas the difference in eccentricity between both orbits creates what's known as the in-plane motion. Okay? So a couple of things here I just said that are important as well is that the LX, LY plane is known as the in-plane motion, whereas the LZ direction is known as the cross-track motion, or out of plane motion. Those two things are synonyms, okay? Furthermore, I'm going to refer from there on to the LX direction as the radial, if I'm not mistaken. I forgot where that is in the notes, but long track, radial. Yeah, that would be the radial direction. And where LY on its own is the long track direction. Whew, okay. That was a lot. We're not done yet though, okay? Let me keep going through the very last subsection of this entire course, which is all about designing specific formations based on what we know already. Okay? So, I was going to ask, are there any questions? It's just a habit that I have, but obviously it doesn't work for online lectures, doesn't it? So, formation designs. In 5.3.3. 5 of them, okay? So, first one is referred to as the in-plane elliptical formation. So here, instead of having a three-dimensional motion, that when it is projected in the LX, LY plane, draws an ellipse, and all we have is an actual ellipse in the LX, LY plane with no cross-track motion or out-of-plane motion, okay? So, I think I have to illustrate all of them because I have placeholders for figures. Yeah. Again, I'm just going back to my LVLH reference frame. Lx, Ly, Lz, and hopefully by now I don't have to draw the target spacecraft at the origin. This is kind of known, hopefully by now. So all I want to do is to select the initial conditions, because as a designer, that's all I have to in terms of freedom to play with, right? Just by carefully selecting the initial conditions at t equals 0, or in other words, where do I locate the chaser spacecraft with respect to the target? Now, which velocity do I let it go with respect to the target object will give me different formations, okay? So again, this is all through careful selection of the initial conditions. What I want to achieve here is an ellipse in the Lx, Ly plane around the target object with no cross-track motion. Well, that's kind of easy because I know already how to select two of those initial conditions. Those two were selected previously to cancel the linear drift in the y direction of LVLH, and to ensure that the formation is centered around the target object, which is what I want to do with an in-plane elliptical formation. So I'm going to just repeat what we had discovered previously. So i.e. the initial conditions along y in terms of position and velocity. And because I don't want to generate any out-of-plane motion, I don't want that oscillatory behavior to take place, it means that I have to specify the initial position along Lz equal to the initial velocity along Lz to be exactly equal to 0. Okay? So just by selecting those 4 initial conditions, or making sure that my initial conditions satisfy those 4 relationships, I will for sure generate that kind of relative motion, or the 2 orbits that are going to be generated from the ECI perspective will draw an ellipse if you were to be sitting on the target spacecraft observing the other spacecraft, which is a chaser, orbiting along its orbit, which comes close to you and further away from you at some other time, okay? So along one big ECI orbit of the target spacecraft, the chaser would draw one relative orbit like that. Okay? So, because you have 4 equalities to satisfy, it means that you only have 2 parameters left. And those 2 could be chosen in any way you want, because those 2 remaining would only define the size of the relative orbit. Yes, and the position at t equals 0 of the chaser spacecraft along this relative ellipse. How? Well, through what we had previously in terms of A naught, which is x naught dot over n square of this plus x naught square, square root of all that, and then alpha, the third integration constant of our reparameterized closed form solution for the differential equations of motion. Whew, that was a mouthful. Okay, we saw previously that that was just inverse tan of minus x naught dot over n x naught, like this. So it's up to you to select x naught and x naught dot to generate the size you want for the ellipse, and to make sure that the spacecraft starts along this ellipse at the location you want through this third integration constant here. Based on your selection of x and x naught dot, then you calculate those 2 and you apply those 2 conditions as well, and you're going to get the relative ellipse with the size you want in LVLH. As easy as that, okay? So that was kind of the most trivial, or, well, that was an easy one to design based on what we had just determined previously, and that was that the motion projected in plane was the ellipse, and that the motion with the outer plane was the oscillator. If you want to have in-plane elliptical formation only with no cross-track motion, cancel the outer plane motion, make sure you are centered at the target, and make sure there's no drift. And just by virtue of the equations, you're going to generate this ellipse. And you set the size you want to x naught and x naught dot. All right? So hopefully that summarizes quickly the first formation design that you can apply. Again, keep in mind here that everything we do is based on our assumptions, because all those initial conditions are selected based on the solutions of the linearized differential equations of motion. But in practice, or in reality, the relative motion between two spacecraft on orbit is nonlinear. Remember that the exact equations of motion we had obtained in the first place were the nonlinear ones, while those corresponds exactly what's going to happen on orbit, neglecting orbital perturbations. But if both spacecraft happen to be close enough and far away from M1, then the linear approximation works well, and therefore those initial conditions would almost generate the ellipse, for example, we were looking for in the first formation design. But if you want to maintain that ellipse over, say, 100 orbits, you need to actively correct the trajectory to maintain that ellipse, because passively, just by selecting the initial conditions and being hands-off, would generate that ellipse for a couple of orbits, but after time, the perturbations like drag would mean that one of the two spacecraft would have its semi-major axis changing more rapidly than the other one, and therefore the orbital energy won't be the same anymore, and thereby it would start to drift. So you need to actively correct this drifting motion with propulsive maneuvers, but this concept is beyond the scope of this course. But this is what we do on a daily basis in the lab. We derive control systems that are designed specifically to maintain a given type of formation, regardless of any perturbations that are affecting both spacecraft, and regardless of uncertainties in the spacecraft mass, and so on and so on. So that's kind of one branch of the research within the lab, as I've described back then, way back then in the introductory video with the slides. Of course, I had talked about the research within the lab, and one branch was formation flying. Well, that's what we do. We design control systems that are intelligent and adaptive and smart enough to make sure that the relative motion stays bounded through active control or through propulsive maneuvers, regardless of perturbations that would naturally tend to make both spacecraft drift apart, regardless of what you choose for the initial conditions, okay? But here, for the purpose of this course, we are assuming that just placing the chaser spacecraft at a specific location initially with respect to the target and pushing it with some initial velocity with respect to the target in whatever direction is sufficient to generate passively or hands-off a given formation. Okay, close the parentheses. So that was the first formation design achieved by careful selection of initial conditions. Now the second one is the along track formation, which is the dumbest of all formations in my own opinion, because all you have is both spacecraft along the same orbit, yet separated by some true anomaly difference, like that. Target, chaser, and that's all you have. Okay, so if that's indeed what you want to have, the trick to do it is just to offset the chaser spacecraft with respect to the target in the y direction. Be either positive if you want to place the chaser ahead of the target, or negative if you want the chaser behind the target, such that x naught is going to be equal to z naught equal to x naught dot y naught dot equal to z naught dot, and all of this equal to 0, such that if you plug these 5 initial conditions in the closed form solution, you're going to get the solution for x, y of t, and z of t, something very boring, which is just x is going to be equal to 0. The initial offset that you're going to select along the y direction of LVLH, right? This is Lx, Ly, so along this direction is going to be a constant in the y direction and with no out-of-plane motion on top of that. So it's just in the long track because this is a relative motion only in the along track direction. So if you were to look at the time history of y versus time, it would just be a constant. And x and z would always be at 0. So the chaser would be 50 meters behind the target forever. And that's it. Very boring, yet very simple to achieve. And as a designer, again, the free parameter you can design with is y naught, which is the offset in this direction. And you could also relate this y naught to the difference in true anomaly you want. And here we're going to take the approximation that this side of the triangle simply delta theta times the semi-major axis. Okay? This is an approximation, of course, but I will explain in practice. So if you know the size of the circular orbit you're dealing with, and you know the offset in terms of true anomaly that you want, you can calculate the y naught that will correspond to that, and set y naught to be this value or whatever value you want, and set alligator wants to be 0 at t equals 0, and boom, you're going to get the chaser ahead or behind the target constantly, okay? So it's kind of boring, but for completeness, I gave it to you as well. Okay, let's look at quite a bit more complex formation that is going to be difficult for you to wrap your head around. But I'll do my best because this involves 3D drawings, and as you know by now, my 3D drawing skills aren't the best around. Okay, this one is known as the in-track formation. Although the along-track formation was the most boring and the most simple one around, the in-track formation is probably the most evolved formation you can think of. So this one is designed, I'm going to do my best to put it in words, to ensure that both spacecraft that are riding along their respective orbit, and i.e. their orbits are along 2 different orbital planes, are such that both spacecraft would fly over the exact same spot on the Earth at 2 different times. Okay? For example, spacecraft 1 and spacecraft 2 are designed to both fly over Ottawa 2 minutes apart or 2 hours apart. Okay? So that is the key idea behind designing the in-track formation. To make it happen, and this is where it's going to get complicated, to make it happen, you need to, if this is the Earth, the equator, and the target spacecraft, and let's just pick a point okay, this is one orbit, and the other orbit would look, say, something like this. No, they share the same right ascension of ascending node. Oh, I knew it's difficult to draw orbits in 3D sometimes. So Earth, one orbit, with its own right ascension of ascending node. But I need to draw another orbit that has a different right ascension and ascending node. So how would that look like? Cross the equator somewhere here. This one, if I do. Oh boy. Something like that. Okay. So what you have here are two orbits that have different rayan. Okay. Because rayan is the angle between IX and the line of ascending node of both orbits, and obviously because they aren't the same, well, rayan isn't the same. Okay, so if you want, and the reason why you need an offset and right ascension of ascending node to ensure that both spacecraft fly over the same geographical spot on the surface of the Earth yet at two different times is because the Earth is spinning underneath the inertially fixed orbit. Okay, so say spacecraft 1 let me think, Earth is spinning this way, so spacecraft 1 fly over, say, Ottawa at some t, time equal to t. While here, spacecraft right over Ottawa sees us, wave at the spacecraft, still over here. It says t equal, time equal t. And then we want the other spacecraft of the formation to also fly right over Ottawa, but at some time in the future. Which means that the second spacecraft must be behind the second one whenever this one is right over Ottawa, such that once this one is past Ottawa and flies up to the north, as the Earth rotates, the spacecraft would advance and eventually hit the same latitude that the spacecraft 2 was sometime in the past. Okay, so that was at t, and now this is t plus some delta t, and that one at this future time is now further north. This one is right over Ottawa, and the reason why it is like that is because Ottawa moved eastward in that amount of time. So you need to separate the orbit according to the delta time at which you want both spacecraft to fly over the same spot. And that separation is being translated by a change in the right ascension of ascending node. Okay? Because if they would share the same rayan, yet spacecraft 2 behind spacecraft 1, it will be impossible for them to fly over the exact same spot. Because spacecraft 1 would fly over Ottawa, and whenever spacecraft 2 would reach the same latitude, well, Ottawa would be right here. So here we could look at, I don't know, somewhere in Saskatchewan, for example, okay? Because again, the Earth spins underneath the orbit. Hopefully that's kind of clear-ish, and hopefully this 3D diagram didn't make things worse. If it did, well, apologies. Guilty as charged, but I did my best, okay? So this, in terms of equation, translates into, first up, a difference in the rayan between both orbits that is going to be equal to the angular rotation of the Earth, which is a constant. That's your 2 pi per day in radians per second, times the time difference over which you want to fly over the same geographical spot. Do you want to fly over Ottawa over a delta t of 1 hour, meaning that spacecraft 1 flies over Ottawa, and 1 hour later we see spacecraft 2 flying right over us, or 2 hours, or 30 seconds, I don't know. That's the delta T you want for the exact same spot in terms of visibility from the spacecraft, okay? And this delta T could be translated into a delta true anomaly, okay? Because the perigee of both spacecraft would be a good idea to be located at the same spot in terms of the distance from the line of ascending node. Okay, so say perigee is here, perigee is here. So that is argument of perigee spacecraft 1 and argument of perigee spacecraft 2. So they would be the same. Yet you want a difference in true anomalies, or a difference meaning that spacecraft, chaser spacecraft needs to be ahead or behind the target spacecraft to make sure that we take into account the rotation of the Earth, and that delta true anomaly is related to the delta time just by the n factor, and because of the convention to measure delta true anomaly, we're going to just put the minus sign here, okay? And this delta true anomaly could also be related to the offset along the Ly unit direction, right? If one spacecraft is behind another one, it means that there has to be an offset in the along track direction, which is related to an offset in true anomaly. And as we've done previously with the triangle assumption, we're going to use it again and say that this offset in true anomaly turns out to be the initial position along y direction over a, so that's your delta true anomaly, and then over n for the delta time. Okay? Whew. This is the difference in Rayan. Now, in terms of initial conditions, Cartesian initial conditions, because that would be a difference in orbital elements, which is kind of the most intuitive way to visualize things, but this translated in terms of x, y, z naught and x, y, z naught dot turns out to be equal to x naught equal x naught dot equal y naught dot equal z naught dot equal to 0, and we want the offset in the cross-track direction, right? This is seen from that perspective. The along track is along the orbit. The radial direction will be towards you, from the center of the Earth to the spacecraft, kind of towards you. And the z unit direction will be normal to the orbital plane, and we clearly see that we need to have an offset in this direction. And this offset along the cross-track direction could be calculated by the angular rotation of the Earth, omega Earth, over the mean motion times sine of inclination times y naught. Okay, I'll spare you the details to calculate this, but just keep in mind that that's what you need to select. Those equalities have to be satisfied. So again, as a designer, what you have control over is the initial offset in the along track direction, which is related to you as a designer, to the selection of the delta t, or the time difference at which you want both spacecraft to fly over the same geographical spot on the surface of the Earth. Okay? So that has some very useful Earth observation benefits in terms of practical advantages, and one of which is to be able to image the exact same spot at 2 different times of the day. So maybe early in the morning image of Ottawa, and then followed by late afternoon image of Ottawa, to compare, say, I don't know, the heat signature of the city as a lot of cars are driving around and things like that, or to analyze concentration of CO2 in the atmosphere of Ottawa at 2 different times of the day using two scientific satellites, things like that, okay? So that would be the practical application of this in-track formation. Easy peasy, because as a designer, all you have to do is to make sure that these are satisfied and that you select why not according to the delta t time you want. Real quick over the last two formations, because this lecture is, I think, turning out to be a long one. But because this is a lot of fun, I know that you don't mind a long lecture, especially for the last one, right? We love formation flying and we don't want to let it go. We don't want this to end. Turns out, unfortunately, this will have to end very soon. But the good news is that you can continue at the grad level and come work in my lab as a grad student, master's student, and then eventually PhD student, and then become a doctor in aerospace engineering, specialized in spacecraft guidance, navigation, control. Okay? Anyway, it's getting late, so I'm losing my train of thought here. So the third formation you can design just by looking at the initial conditions of the closed form solutions for the Hale differential equations. It's a circular formation. Is that the third or fourth? This is the fourth, actually. We had the in-plane ellipse, we had the along track, the in-track, 1, 2, 3, that's the fourth one, yes. What you want here is to generate a three-dimensional motion around the target object that would look like a sphere, okay? Such that the constraint you have to satisfy is that x squared plus y squared plus z squared must always be equal to the radius of your three-dimensional sphere squared. So 3D circle, essentially. That's what it is. In order to satisfy this, obviously you want the motion. You want the motion to be centered at the target, and you don't want any drift. So you apply the same conditions with these two, minus 2n x naught and 2 x naught dot over n. And this is where the two other initial conditions have to be satisfied to generate this circular formation, and that is plus minus square root of 3 times x naught, and here plus minus square root of 3 and times x naught dot. Okay? Now the plus minus only depends on if you want that is the plane in which you want. Yeah, no, sorry about that. I began this one wrong. You're not generating a 3D sphere, you are generating a 3D ellipse for which the projection on a given plane happens to be a circle. And that plane is inclined. So if you were to look at the motion from the back, so this is Lx, and that is Lz. So you are looking straight at the along track direction. You would see the circle plus 30 degrees. So either along this plane or along this plane. Okay? So this is for the plus square root 3 x naught and plus square root 3 x naught dot condition that would generate the circle in that plane. That would generate yeah, the projection of the 3D motion onto that inclined plane, which is 30 degrees from this, is generated by selecting the plus conditions here, and the last one is at minus 30 degrees. It's generated whenever you select the minus square root of 3 for the initial conditions about z unit direction, like this, okay? So because you need to satisfy these 4 conditions as a designer, you can select the x naught and the x naught dot conditions to be whatever you want them to be, and actually those are related to, surprise, surprise, the size of the circle you want to see in 3D, right? And that relationship is that x naught is related to half of the circle radius times cos of lambda, and x naught dot is actually minus r times n over 2 of sine of lambda, where lambda is the, stay with me, the initial position of the spacecraft projected onto this plane and measured counterclockwise from the cross-track direction. That is a lot. So if you were to look above at the motion, you would see Lz and Ly towards now my right, and the initial angle of the initial position corresponding to the initial position of the spacecraft onto that plane is measured counterclockwise from this direction. So that's your lambda angle. Okay? So this is the circular formation, and this was probably confusing, but the best thing you could do for yourself to visualize those 3-dimensional relative motion is to simulate them, okay? And actually, as a separate or a bonus video that I am going to be posted on the web for you guys, is that I'm going to be walking you over the process with which I simulated those relative motion in MATLAB Simulink, and the output of my simulations are actually motions on a graph. So you'll be able to see the motion evolving with time in 2-dimensional space as opposed to just static graph. So hopefully this will shed some light or will help you gain a better understanding of those 5 bounded relative orbits that we can generate by solely cherry picking the initial conditions we want. Okay? And the very last one is the projected circular formation. Circular formation, widely referred to as PCO formation. So the difference here is that the motion, if you go back to the circular formation, the circle was seen in a plane inclined at plus minus 30 degrees, okay? But here the plane would actually, or the circle would appear in the YZ plane. So as seen from the ground, if you were to look at the relative motion of the chaser with respect to the target, you would see a circle in this plane. Okay, so the projected circle is taking place in the YZ plane, such that you now have to satisfy this constraint equation. And same old, you have 4 initial conditions that are set in stone. The first 2 to cancel the drift, and the other 2 to generate the circle in the XZ plane, or the YZ plane, sorry. and that is done through the Z initial conditions are going to be equal to plus minus 2 x naught and plus minus 2 x naught dot. Okay. Again, the plus minus corresponds to the plane in which the 3D ellipse takes place in. So the plus here corresponds to a plane inclined at 26.565 degrees seen from the back. So this is your LX radially out. This is LZ normal to the plane, and LY is into the board. So now the plane in which the 3D motion takes place, so in other words, the chaser spacecraft is limited to move along this plane or along this plane, 3D wise, and would draw an ellipse, okay, in this plane or in that plane. But then the projection of that ellipse in the YZ plane, so the projection of an ellipse here, would give you a circle as seen from above, okay? And the angle in which the actual motion is taking place is either plus minus 26.565 degrees from here. And if you were to choose the minus initial conditions, that would give you the other plane in which the actual 3D motion would take place, which would be this plane of motion, okay? And I think that this explanation in terms of the plane of actual motion in which the ellipse is drawn was a better explanation than before. But again, don't worry too much at this point. When you will get to see them in simulations, and in terms of animations, you will get a better understanding of how things move with respect to LVLH, okay? And finally, as a designer, you have control over those two initial conditions, x naught and x naught dot. And again, those are only selected to generate the projected circle with the appropriate size, starting with the spacecraft, the chaser spacecraft, in the appropriate location along that circle. And this is x naught dot equal to minus Rn over 2, and then sine of lambda. Okay? So section 5.4 is kind of beyond the scope of this course. This is all about active control of a chaser spacecraft to ensure that it follows whatever type of bounded orbits, regardless of perturbations that would be tending to naturally drift both spacecraft apart. So you need to actively correct for those kind of perturbations. And I've kind of laid out a generic methodology to design a feedback control system that would ensure that the chaser spacecraft is actively tracking the relative motion you want as a designer. Feel free to read through section 5.4. It won't be in any exam, but if you wish to continue at the graduate level in this field of study, it would be a good kind of introduction to active feedback control, specifically applied to spacecraft formation flying. But as usual, I'm going to be available to answer any questions you might have about section 5.4, either by emails or during one of the live Q&A sessions. So, ladies and gentlemen, this is with great sadness that I'd like to announce that this is the end of this course. It's been quite a bit of a ride. It's been a lot of fun for me. I really hope that you've learned a lot and that this course met your expectations about the Aero Stream D, that you are just beginning, because up to now we're just taking some generic courses in Mech and Aero. So that was your first Aero D specific course. I've put my heart into putting the lecture notes together. I've put my heart into delivering what I think is high quality lectures with my homemade studio here with the crappy lighting, crappy microphone. But it was a real fun for me. So wishing you the best of luck for the final exam. All the best in your future career as spacecraft engineer. And Looking forward to meeting you in person one day. Take care, guys. See ya.